All right, let's talk about one of the most elegant and frankly powerful tools in all of abstract algebra, the class equation. You can think of it as a special key, one that unlocks the hidden internal structure of finite groups. So, let's start with the big question. How would you even begin to map a universe? I want you to imagine a finite group not just as a list of elements, but as this vast, sprawling universe with its own weird laws and hidden structures. Where do you even start? And that's the real challenge, right? These finite groups can be mind-bogglingly complex. We desperately need some kind of map, a guide to chart their internal landscape, so we can really get a grip on their structure. And that, right there, is exactly what the class equation gives us. Okay, so the very first step in mapping this universe is to figure out how to sort all of its inhabitants, all the elements of the group, into meaningful collections. You can think of it like finding all the different cliques or families that exist inside the group.
This brings us to our first huge idea, conjugate elements. We say two elements, let's call them A and B, are conjugate if you can turn A into B by using some other element G from the group, like this, B equals GAG inverse. Now, the really cool way to think about this is as a relabeling. The element G is kind of like a translator. It changes your perspective, but the deep underlying structure of the operation remains exactly the same. So A and B are basically structurally identical, just seen from a different point of view.
What's amazing is that this relationship of conjugacy neatly partitions the entire group. The set of all elements that are conjugate to some element A is called its conjugacy class. These are the cliques, the families we were looking for. Every single element in the group belongs to exactly one of these classes. It's like we've perfectly sliced the entire group up into these distinct, non-overlapping families.
Now, within these groups, some elements are, well, they're a bit special. We call this collection the center of the group, or Z of G. The center is the set of all elements that get along with everybody. They commute with every single other element in the group. For an element x to be in the center, it has to satisfy xg equals gx for every single g you can find. They're the ultimate insiders.
And this is where things get really interesting. If an element x is in the center, what happens when you try to conjugate it? Well, G inverse just simplifies right back down to x. It doesn't change, so its conjugacy class is just itself. It's a lonely little clique of size 1. Every other element that's not in the center belongs to a bigger family, a class with more than one member, because there's at least one other element out there it doesn't commute with.
All right, so we've sorted all our elements into these nice family groups. Now it's time for the masterstroke. We get to reveal the equation itself, and it turns out to be this beautifully simple act of just counting.
And here it is, the class equation. It just says that the total number of elements in the group, its size, Ig, is equal to the size of the center, Izg, plus the sum of the sizes of all the other distinct conjugacy classes. I mean, think about it. Since these classes are just those disjoint families we found, this equation is really just a simple accounting identity. We're just adding up the sizes of all the little cliques to get the size of the whole group back.
Let's make this real. Take S3, the group of symmetries of an equilateral triangle. It has 6 elements in total. Its center is just the identity element, so that's a class of size 1. Then, the 3 reflections form one class of size 3, and the 2 rotations form another class of size 2. And what do you know? 1 plus 2 plus 3 equals 6. It works perfectly. Okay, how about another one? D4, the symmetries of a square. This one has 8 elements. Its center actually has 2 elements. The other 6 elements fall into 3 different classes, and each of those classes has a size of 2. So for D4, the equation is 8 equals 2 plus 2 plus 2 plus 2. You see? Different group, different structure, different partition, but the same elegant counting principle holds true.
Okay, so this is a really neat counting trick, right? Well, it is so much more than that. This simple little equation has some absolutely profound consequences. It's the key that lets us unlock some of the deepest secrets in all of group theory.
Now, to really see its power, we have to talk about a special kind of group, a P group. A finite group is a P group if its total size, or its order, is a power of a single prime number P. So for instance, a group with 8 elements is a 2 group, because 8 is 2 to the power of 3. These P groups are like the fundamental building blocks of finite group theory.
Okay, watch the class equation go to work. We can prove that any finite P group has to have a non-trivial center. Let's just walk through this.
First, we start with the class equation. The size of the whole group equals the size of the center plus the sizes of all the other classes. Second, a key theorem in group theory says that the size of any conjugacy class has to divide the total size of the group. Since our group size is a power of a prime p, that means the size of every single one of those other classes, ni, has to be a multiple of p. So step 3, think about that. The left side of our equation, by g, is divisible by p. And the sum of all the ni's is also divisible by p, because each part of the sum is. The math just forces the last remaining piece, the size of the center, by z of g, to also be divisible by p. And finally, we know the center is never empty. It's always got the identity element, so its size is at least 1. If its size is a multiple of p, it has to be at least p. And there it is. The center is non-trivial. What a beautiful, simple, and powerful argument.
And that's just the tip of the iceberg. That same line of reasoning is the absolute cornerstone for proving a whole bunch of other monster theorems. It helps us show that any group of order p squared has to be abelian, meaning everything in it commutes. It's essential for proving Cauchy's theorem, and it's a critical ingredient in the mighty Sylow theorems, which give us this incredibly detailed blueprint of a group's internal structure.
And get this, the equation's influence reaches way outside of basic group theory. It's a key part of the proof for Wedderburn's little theorem. This theorem says that any finite division ring, which is like a field, but where multiplication doesn't have to be commutative, actually is commutative after all. It's this incredible result that basically proves you need some kind of infinity for non-commutivity to exist, and the proof relies on a tool that started out as just a simple way of counting things.
So, after all that, what's the big picture? Why does this one little equation matter so much? Well, it really comes down to the power of abstraction.
What the class equation really shows us is how a beautifully simple idea, just splitting a set up into families and counting the parts, can unlock these profound hidden truths about incredibly complex structures. It proves that our initial search for a map was the right one all along. By charting the group's landscape this way, we can navigate its hidden universe and actually discover its fundamental laws. This really gets to the heart of what makes math so powerful. So I'll leave you with this to chew on. What other profound truths in math, or maybe even somewhere else entirely, are just sitting there, waiting to be discovered, hidden behind a simple act of counting?